Today we're going to have a look at distance time graphs and velocity time graphs. We'll see how we can interpret distance time graphs. We'll have a look at how we can calculate acceleration using the equation a equals v minus u over t. Once we've done that, we'll have a look at how we can analyze and interpret velocity time graphs and the two things that we can actually get out of velocity time graphs. Before we go any further, we need to have a look at this equation. Speed equals distance divided by time, or maybe you'll think about it as distance equals speed times time, or time equals distance divided by speed. However you decide to remember it, it's absolutely fine. So the triangle would have a d on the top and st on the bottom. We measure speed in physics. We normally use meters per second. So if you're given values in kilometers or minutes or hours, you're going to need to convert them to get down to the regular standard units, which are meters per second. We're able to find something's speed if we know how far it travelled, that's the m bit, and we know how long it took to get there, that's the s bit. And when you divide that distance by the time, the sum that you do, the calculation that you perform, is those meters divided by seconds, so m divided by s. Now this is actually the units for speed. The units for speed are meters per second, or m divided by s. So the units actually give us what the equation is. If we want to find the speed, it's meters divided by seconds, m divided by s. Let's have a look at this example. A bus takes some children to school. For the first 20 seconds of the ride, it travels at a constant speed over the course of 100 meters. The bus then stays stationary, so it's at rest. There's no speed, no velocity. And it stays there for 10 seconds. For the next 30 seconds, the bus accelerates, and it does this for the next 150 meters. Now, I'd like you to pause the video, and I'd like you to sketch out the axes that I've got here. I'm just sketching, you don't have to do it too neatly. See if you can draw what this might look like. So for the first 20 seconds, the bus was traveling at a constant speed and did this for 100 meters. We'd have a straight line for that. So it's going from 0 meters up to 100 meters, and from 0 seconds up to 20 seconds. It's a constant speed, so we've got a nice straight line there. It's then stationary, it stops, it's at rest for the next 10 seconds. On a distance time graph, we show that with a straight line, flat across, a straight horizontal line. So for 10 seconds, for 20 up to 30 seconds, the line is flat and horizontal. No distance is being covered whatsoever. We're staying at 100 meters. It is stationary, it's staying there. We have a lovely flat line. The next 30 seconds, the bus accelerates over 150 meters. If anybody actually got this, I'll be very impressed. What we would have here, in fact, would be a curve. Now, this curve shows that it's accelerating. Its velocity is increasing. This first line we had here was for a constant speed, so the same amount of distance being covered each second. When something is accelerating, its velocity is increasing. The number of meters traveled per second is going up. So, for instance, for the first 10 seconds, we travelled, what's that, about 12.5 meters. But for the 10 seconds after that, we travelled about 37.5 meters. And for the 10 seconds after that, 100 meters. So we're actually going faster and faster. The speed is increasing. And we show that on a distance time graph with a curve. You can get a pretty good idea of the motion of an object by looking at a distance time graph. The three things you can actually tell are whether it's moving with a constant speed, the blue line here, whether it's at rest, so stationary, which is the green line, or whether it is accelerating, which would mean a curve like this. So a diagonal line would indicate a constant speed, a horizontal line would indicate that it's at rest, and a curve would indicate that it is accelerating. The other thing that you can tell from a distance time graph is how fast an object is moving. And we're going to use our equation d equals st to find this out. Let's see if we can find the answers to these two questions. Where is the object moving fastest, and how can you tell? And the second question, how fast is it moving in the fastest section? So pause the video, have a bit of a go, and then when you've got your answers, play again. The object's moving fastest in between C and D, and we know that's the case because that's where the line is steepest. In between C and D, the object is travelling a fair amount of distance. It's going from 40 up to 100 meters, so it's traveling 60 meters. 100 minus 40 is 60, and it does that in 5 seconds. In between B and C, also takes 5 seconds, but it only goes from 10 meters up to 40, so only 30 meters. So it's not traveling as far in that same length of time, so its speed must be slower. So we can tell when an object is traveling fastest because it will have the steepest line for distance time. Second question, how fast is it moving in between C and D? Well, we're going to use what I like to call ERNU, so this is a way of answering mathematical questions in physics. The E stands for equation. Which equation do I need to use? The R stands for rearrange. Do I have to rearrange my equation? The N is the numbers that you need to put in. And the U is your answer, not forgetting the units. So ERNU is the way to answer these questions. We'll do this throughout this lesson. The equation I'm going to use is D equals ST. Distance equals speed times time. I'm going to rearrange it like this. Speed equals distance divided by time. The numbers I'm going to use, well, for my D value, I'm going to use 100 minus 40. So that's the distance that it ends up at versus the distance that it started at, 100 minus 40, which is 60 meters. And for the time, I'm going to do 15 minus 10, which is 5 seconds. So to find my speed, I'm going to put 60 over 5. 60 divided by 5. 60 divided by 5 is 12. So the speed that it's traveling is 12 meters per second. Between 10 and 15 seconds, there's C and D. That means that the person or the object is covering 12 meters every second. What we've really done there is we found the gradient of the line. The gradient of a line we normally find by doing the change in y divided by the change in x. We did the change in y, which was 100 down to 40, so 60. And the change in x, which was 15 down to 10, so 5. So we did 60 over 5. The gradient we've calculated was the speed, meters per second. The y-axis was measured in meters, and the x-axis was measured in seconds. So we did the change in the meters divided by the change in the seconds. We did meters divided by seconds, which is what gives us speed is meters divided by seconds. This is the graph of a girl walking to school, showing the distance that she travels over the course of time. Pause the video and see if you can describe her motion and put in as much detail as you possibly can. The kind of things you should include should be numbers from the graph. Use the data that's available to you. Tell us when she was fastest. Tell us when she was slowest. Work out the various speeds that she had over the course of the journey. And make sure that your answer is in a logical order. So start at the beginning and end at the end. Pause the video, have a go. So, as we've said, it should be in a logical order, so let's break it down section by section. Let's start with the journey from A to B. Well, from A to B, the girl walked 200 meters, so it started at 0, went up to 200, so 200 meters were walked, and it took 40 seconds to get there. Her speed then was 200 divided by 40, so meters divided by seconds, giving a speed of 5 meters per second. Next section, B to C. Well, B to C, we have a flat line here on the graph, and a flat line would indicate that she is not moving at all. She's stationary or at rest. She's covered no distance in those 40 seconds, and again, we've used the data we've got there from 40 up to 80 is 40 seconds, so her speed is 0. From C to D, the next section, well, we're off again. We're moving again. We have a gradient to this line. It's a steep line. The girl walks 150 meters, so she goes from 200 up to 350, so 350 minus 200 is 150 meters, and it takes 40 seconds. 120, 80, 40 seconds. Her speed was 150 divided by 40, so 3.75 meters per second. The last section, D through to E, she walks again 150 meters. She goes from 350 up to 500, which is 150 meters. This time it takes her 140 seconds. It's from 120 to 260. The difference then is 140 seconds. Her speed then is 150 divided by 140. Not a nice number. You're going to get a weird looking decimal on your calculator, but we can round it to 1.07 meters per second. The last thing that we haven't included are when she was fastest and when she was slowest. So she was fastest in between A and B, where her speed was 5 meters per second. And she was slowest in between B and C, where her speed was 0 Let's move on and have a look at how we can calculate acceleration using a equals v minus u over t. Acceleration is the rate at which an object changes its velocity. Now, we've been through this before in previous lessons. We've had a look at what velocity is. Velocity is just speed in a given direction. Velocity is vector, meaning that it has size or a magnitude, as well as a direction. Speed is just the number. Speed just has the magnitude. So velocity, you can think of it as speed, but in a given direction, and it has the same units, meters per second. If something changes velocity quickly, it has a high acceleration. Now, the story of the tortoise versus the hare. The tortoise has a very slow acceleration, takes a long time to get up to its full speed. The hare, though, can accelerate very quickly. It can go from 0 to a lot, quite fast. Three things that we need to know in order to find out an object's acceleration would be: how fast was it at the end of the time that we're looking at? How fast was it at the start of the time we're looking at? And how long did it take to get to that new speed? Now, we call acceleration A. Acceleration is measured in meters per second squared. And like I said, we need to know how fast it was at the end of the time period we're looking at. We call that v. Final velocity, we call that v for short. That's measured in meters per second. We also need to know how fast it was at the start. We call that the initial velocity. Initial just means the beginning, like your initials, they're the beginning letters of your name. Initial velocity, we call that u for short. That's also measured in meters per second. And the last thing we need is how long it took to get up to the new speed. And that time, t, short, and that's measured in seconds. So the equation that we have is a equals v minus u over t. How fast was the object at the end of the time we're looking at? How fast was it at the start? And how long did it take to change, get to that new speed? V minus u, the change in the velocity, divided by t. Our hare is going to start the race with a velocity of 0. It's at the start line, it's not moving yet, has no velocity. Then takes 2 seconds for him to accelerate up to 24 meters per second. What was the hare's acceleration? Pause, have a bit of a go, then unpause to see if you got the answer right. Again, I'm going to use ERNU, E for the equation. That's the first step in answering questions like this. R, do I need to rearrange my equation? N, put in my numbers, and U, give an answer, but don't forget units. The equation I'm going to use is obviously A equals V minus U over T. I don't need to rearrange it, so I can go straight into putting in the numbers. The V, final velocity, was 24 meters per second. The U, the initial velocity, the starting velocity, was 0, so 24 minus 0, and the time that it took was 2 seconds. So we end up with 24 divided by 2. 24 divided by 2 is 12 per second squared. So the hare accelerated 12 meters per second squared. All right, one way that I like to think about that is 12 meters per second a second. The reason I like to think about it like that is that it tells me what acceleration is. Something increases its speed by 12 meters per second per second. That means that at the beginning it might have 0, in the case of our hare here, but after 1 second, it would have increased its speed by 12 meters per second. After 2 seconds, it would have increased its speed by 12 times 2, 24 meters per second, which is what we see here. After 2 seconds, he's accelerated to a velocity or a speed of 24 per second. Second question, the tortoise gets to the end of the race. And the tortoise takes quite a long time to slow down. It's going to take him 8 seconds to slow down from 4 meters per second to come to stop, to come to rest. What was the tortoise's acceleration? Pause the video, have a go, unpause and see if you got it right. Once again, we've got ERNU in here. We've got the equation we're going to use. Do we need to rearrange it? Put in the numbers, give an answer without forgetting the units. The equation again is A equals V minus U over T. We don't need to rearrange it. The numbers we're going to put in, now this is where people often fall down, and you may well have made this mistake yourself. The final velocity, the V, is 0. He's coming to rest. He's slowing down to a stop. So his final velocity is 0. The velocity at the start of the time period we're looking at was 4. So we're doing 0 minus 4. Time taken was 8 seconds. So 0 minus 4 over 8, which is minus 4 over 8. Minus 4 over 8, which means that the acceleration was negative 0.5 meters per second squared. Now that negative means that the velocity was decreasing. Remember, velocity is vector, meaning that it has a direction as well as a magnitude. Now we tend to assign one direction as being positive and one direction as being negative. And because he's slowing down, we would assign that as the negative direction for that. So negative 0.5, he is decelerating rather than accelerating. Last thing then we need to look at is how to interpret velocity time graphs. These two graphs down here look on the face of it to be pretty much identical, but they are not. They actually show quite different things. Graph on the left is a distance time graph. Graph on the right is a velocity time graph. What do they show? Pause, have a bit of a think. Unpause when you think you've got the answers. On a distance time graph, this upwards yellow slope indicates that it's moving away and it's moving with a constant speed. A flat horizontal line like this would show that the object is not moving at all. It's not covering any distance. The distance is not changing, so it is stationary. It is at rest. Now, a line going back down like this would indicate that it's actually coming back towards the place that it started. So it's returning, but the line is still flat, so that's still a constant speed. On a velocity time graph, these shapes mean different things. So an upward straight line like this actually means that the object is accelerating. Its velocity is increasing. Its velocity is going up over the course of time, so it is getting faster. Velocity is increasing, so therefore it is accelerating. A green line, often people say, oh, the green line must mean that it's not moving. No, on a velocity time graph, that means that it has a constant velocity. This is some velocity, and it's not changing, so its velocity is constant, it's unchanging. It is not, though, at rest. Now, this downward slope means that it's decelerating, it's losing velocity, it's slowing down. Its velocity is decreasing, it's going down over the course of time, so it is decelerating. So they are quite different. You interpret them in different ways. Have a look at this. A go-kart gets entered into a race. This graph shows how the velocity of the go-kart changes during the first 40 seconds of the race. Two questions for you. One, state when the go-kart is moving at a constant velocity. And two, use the graph to calculate the acceleration of the go-kart between K and L. Pause the video, have a go, unpause to find out the answers. So the first question was to state when the go-kart is moving at a constant velocity. And that's between M and N. We know that because on a velocity time graph, if you have a horizontal line, that means that you have something moving at a constant velocity. Question two, use the graph to calculate the acceleration of the go-kart between points K and L. Once again, we're going to use ERNU, equation, rearrange numbers, don't forget the units. A equals V minus U over T. Our numbers are going to be 9 minus 5 divided by 12 because we go from a final velocity of 9. We have a starting velocity of 5 and it takes 12 seconds to get there. So 9 minus 5 divided by 12 gives an acceleration of, to two significant figures, 0.33 meters per second squared. When we find the acceleration, what we do is we find the gradient of the line. We're doing the change in y divided by the change in x, velocity divided by time in this case. Here's a question for you. How could we find out how far has been travelled, what the distance travelled was between 2 points on a graph? The way we do that is by finding the area underneath the line. I'm going to show you how we go about doing this. Let's take this simple graph. We have an object that's travelling at a constant velocity of 10 meters per second, and it's doing this for 6 seconds. So it's going at 10 meters per second from 0 all the way up to 6 seconds. First thing we do is we turn this into a rectangle. I'm adding in a line here, and I'm turning this into a rectangle like this. The sides are 10 meters per second here and 6 seconds here. Now, you're not measuring these with a ruler. You're not saying 10 centimeters and 6 centimeters. The dimensions in centimeters or millimeters are not really what we're interested in here. What we are interested in is what this is in meters per second and what this is in seconds. We can then find the area of this rectangle by multiplying the lengths of the sides together. If we multiply velocity and time, what might we get? Remember that velocity is simply speed, but in a given direction. Pause, have a think, unpause. What we end up with is distance. We do speed or velocity multiplied by time, we end up with distance. So if we do the area underneath the graph, we do 10 meters per second multiplied by 6 seconds, we're going to get the distance traveled, which in this case would be 10 times 6, 60 meters traveled. Let's have a look at this one. A cyclist goes for what is, to be fair, an extremely short ride. 3 questions. Question number 1, can you describe the motion of the cyclist? So say what the cyclist is doing. Can you calculate the acceleration in the first 4 seconds? And the third question, can you calculate the total distance that the cyclist travels? Again, pause, have a bit of a go, and then when you're ready, unpause and we'll go through the answers. Question number 1, describing the motion of the cyclist. Well, if we were to describe what the cyclist is doing, we would say that they're accelerating from rest to a velocity of 10 meters per second over the course of 4 seconds. She's then traveling at a constant velocity of 10 meters per second for the next 2 seconds. Question number 2, calculate the acceleration in the first 4 seconds. I'm going to use my Ernu equation. Do I need to rearrange it? Put in the numbers, don't forget the units. The equation is going to be a equals v minus u over t. The numbers are going to be 10 for the v, so the final velocity is 10. The starting velocity or the initial velocity was 0, and the time taken was 4 seconds. So 10 minus 0 divided by 4. 10 divided by 4 is 2.5. 2.5 meters per second squared. The total distance traveled. Now, there are a couple of things you can do here. We know that we need to find the area under the graph, but how you actually go about finding the area under the graph is up to you. Now, option 1 is the one that people often go for. Option 2 looks like it might be more complicated, but actually often is the shorter and easier way to do it. Option 1, first of all, then. Create a triangle and a rectangle on the graph. First of all, find the area of a triangle. The area of a triangle you get by doing half the base times the height. So half times 4, because the base is 4 and the height is 10. So half times 4 times 10 gives an answer of 20 meters. We can then find the area of the rectangle. We do that by doing the base times the height. So 6 minus 4 is 2 on the base, and the height is 10. 2 times 10 is 20. Then all we have to do is add those two things together. 20 plus 20 is 40. So the distance travelled is 40 meters, and that's the correct answer. Now, there is another option. There is another way of doing this. Option number 2 is to create a trapezium. So a trapezium is a quadrilateral. It's something that has 4 sides, but 2 of those sides are an uneven length, resulting in this sloping bit here. Find the area of a trapezium. We do half times a plus b times the height, where a and b are the short and the long sides, and h the height of the trapezium. So plug in the numbers here. We have half multiplied by 6, because 6 is this long side, plus 2, 2 is this short side, multiplied by the height, which is 10 meters per second. So half times 6 plus 2 times 10. Make sure that you get your order of operations correct, and you should come out with the answer being 40 meters, which is the same as this one here. Now, a trapezium is often seen as a bit more daunting than simple triangles and rectangles, but when it comes down to it, that's only one sum you've had to do instead of, well, 3. 1 for the triangle, 1 for the rectangle, and 1 for the adding up. Here you only have one sum, so it's actually a bit quicker if you can get your head around them. Let's return to the go-kart. The one thing we didn't have a look at with the go-kart was how far it travels. So grab a pen and paper, because you're going to need it for this one. Pause the video, have a bit of a go. When you're ready, unpause to see what the answers are. In between J and K, we're going to draw ourselves a line just here to create a triangle. And the triangle's area is going to be half multiplied by the base times the height. So half times 3 times 5, 7.5 meters. So he travels 7.5 meters from J to K. In between K and L, I'm going to draw in another line here, and that's going to create for me a nice trapezium. I have a short side and a long side, and I have a base. Now you may decide to draw in another line along here to create a rectangle and a triangle. You can do that, that's perfectly fine. The trapezium, though, is the quicker option. And between K and L, the trapezium's area is going to be half multiplied by 5 plus 9 multiplied by 12, which gives us an answer of 84 meters. In between L and M, we're going to have another trapezium here. I've just drawn in another line here. I have a short side and a long side, and I have my base. So again, it's going to be half times the short side plus the long side multiplied by the base or the height, whatever the last line is. So half times 9, this is 9 plus 13, multiplied by 15, gives us an answer of 165. Notice what you're essentially doing when you're finding the area of a trapezium is you're just getting the average of these two lengths. 9 and 13 multiplied by half gives 11, so it's the average of these two sides. 5 plus 9 multiplied by a half is 7. So again, it's just the average of these two sides. So you're just getting the average of these two sides and multiplying them by the other side there to give the answer. The last bit then, m to n, just a regular old rectangle. When I draw in my line here, I've got my base, I've got my height. I'm just going to do 10 times 13, which gives me an answer of 130. The last thing then left to do is to add it all together. And it should, when you add it all together, give you an answer of 386.5 meters.